us to talk about quantum computing. So she is a quantum computing researcher and she's now based in Japan. Um, I'm gonna wait maybe a couple more minutes so for everyone to be here. So just 2 minutes. Okay, so now we're live. Thank you to everyone who's here and thank you for joining. We know it's maybe one of those times of the semester where not really everyone has that much free time. But I'm really happy that everyone is here and everyone's super interested. We have a very special guest with us. So Sarah will be joining us to talk about quantum computing. So she is a quantum computing researcher and she's now based in Japan. You'll get to meet her as we move along with this short presentation before we start. Okay, so for those of you who don't know me, I'm gonna go ahead and introduce myself. So my name is Hala. I am DSC lead at our university for this year. So I was selected by Google to create this branch of a Google Developer Student Club at the university. So developer student clubs are essentially Google clubs that they create on campuses to have this sort of community for these student developers and coders, as well as other things. So everyone is welcome to join us. You've probably heard of us already. If you haven't, well, here's your introduction to us. So before we begin, one thing I want to emphasize, we have a zero tolerance policy for harassment of any kind. Please do not join any event with the intent of harassing anyone, engaging in foul behavior, or discriminating um, religion, or anything else. So please keep that in mind. And always try to be as positive as you can. And like I said, we have a zero tolerance policy, so you will not be able to join us for future events if you do engage in this behavior. So just a little about our mission. Our goal is to create impact. So like I said, we're a club that's really backed by Google developers. Our goal is to create impact in our community. So, what type of impact are we talking about? We want you to take our technologies, the coding stuff we teach you, take it to the next level and create things that will empower you within your society and solve community problems. Okay, so that's really all we're about. We bridge the gap between theory and practice. So we really give you all the tools you need to become a good developer, as well as to solve all these problems in your community. But enough about us. So that's really it for now. Our guest of honor is Sara. So Sara Metwalli, she is actually of Egyptian origin. So she is originally from Egypt, and she is now based in Japan. She's from Egypt. She studied in Egypt for her bachelor's, and she got her bachelor's in electronics and communications engineering. She then worked as an Android developer before she traveled to Tokyo to pursue her postgrad studies, and now she's doing her PhD in quantum computing at the Cairo Quantum Computing Hub with IBM. So that's where she does all her research. So, in simpler terms, she's really good at what she does, and she's really into this stuff. So, hopefully, she'll be able to really excite you about this very exciting field. Oops, okay, so I went way ahead. Um, and yeah, that's really it for now. Sarah, I'm gonna leave the floor to you. You can start with your content. Okay.
Okay, thank you. Mm, Okay, we're gonna share my entire screen. Okay, awesome. I hope you can see my screen. Is everything okay, Hannah?
Yeah, we can see. Yeah, we can see. Everything's great.
Awesome. So, good evening, I guess, everyone. For you, it's evening. I am very happy to be here with you today and maybe, as Hala said, get you excited about joining the quantum computing field. It's a very exciting time to join. So today I'm gonna just give a brief introduction to what quantum computing is. If you guys don't know what it is or not sure what it is, or it is right now the field, in case you're curious to join in the future. Before I start, I have a very weird question. I just want to know, like, what is the backgrounds of like the people joining today? Like, are they engineering background, theorists? Like, what is like the average? Because, you know,
Yeah, so I would say maybe like the good majority of everyone joining is in computer engineering, maybe a good half is computer science as well. But you do have
okay,
some new names, new people, so we'll see. We'll see about that.
what's it? Okay, so hopefully it will make sense to everyone. Okay, so let's get started. So Hal already introduced me, so I'm not gonna do it again. So yeah, I'm 28 years old. I'm doing my PhD right now in a research group called AQUA, which stands for Advanced in Quantum Architecture. We are based in Japan, not really in Tokyo, in Kanagawa, which is kind of 2 hours away from Tokyo. Uh, and we do all things quantum from hardware to software. I do software part. I always loved software, never loved hardware really. Although I studied electronics in my undergrad, but it didn't click with me. So let's get started. So what is quantum computing? So I really want this talk to be more interactive than me just talking. So it would be awesome if people can tell me what do they know about quantum computing, or like in a sentence or two. Is that possible, Hala?
Yeah, yeah, I'll let them. So everyone, please drop a comment in the comment box on YouTube where you're watching and tell us what you guys think. So try to answer Sarah's question. So
Yes.
let's see. Let's give them a
So
moment. So in case there is
okay,
any delay on their end.
cool. So the question is, what do you know about quantum computing? Before I started like working on quantum computing, I always thought of quantum computing as, sci-fi to an extent. So it's very cool to know what other people think of it. I mean, whether they do have knowledge of it, they work on something quantum, or they just heard in the
I mean,
news. Hmm.
yeah, I mean, someone suggested we use quantum in computers, which is maybe as simple as it gets.
Yeah.
Yeah. Someone else said it's the future of the world. Someone is saying it's much more powerful than modern computers.
Yes.
Yeah, that's a good point.
Yeah. It's actually very interesting things to hear because, well, quantum is the use of quantum mechanics and physics phenomenons, right? To run, to execute codes or programs or make a computer, right? Unfortunately, it's not the future of computing, not as people think it will be, at least. Hopefully, in the future, we will have quantum computers, but they will never replace the computers that we have right now, which are classical computers. So they always have to coexist because as powerful as quantum can be, there are stuff that classical computers will always going to beat it at. Okay, it's not good, and
Yeah,
it's
that
not absolutely 100% better.
yeah, that's super interesting because I feel like that's a really big misconception. Like, oh, at
Yes.
one point we're ditching our computers, we're moving on. We
No.
do have one more comment I feel which is maybe interesting.
Hmm.
No, actually we have two. The first person
Okay.
said the possibility of having two states of information at the same time, so two bits coexisting. Um,
Yeah.
I feel like we're really getting like towards the technical side. Someone else
Yeah.
said quantum computing is when we use superposition and entanglement to perform faster computations.
Yeah.
Um,
That is a very accurate answer.
okay.
Good person. Clap. It is pretty much that is the basic. We use mechanical phenomena, which is superposition entanglement, to perform computations, right? So that is it. Okay, so let's talk about the superposition in case some of you don't know it. I'm pretty sure everyone heard of Schrodinger's cat. Whether you're in the science field or not, you've heard of it. It's a very famous cat. So the question is, for those who may not have heard it, that you have a cat and a poison in a box, okay? And the box is closed. And until you open the box, you do not know if the cat like played with the poison, ate it, and died, or if she didn't touch the poison or and still alive. Okay, so that's what superposition is. So superposition is that at some point in time, because you don't know the truth, you would think that it's a 50-50 chance. However, once you open the box or interact with it, you're gonna know whether the cat is dead or alive. Okay, so yes, I know this. Everyone thinks, oh, qubits can be both 1 and 0 at the same time. Well, it's kind of true and kind of not. Qubits, which is the quantum equivalent of bits, can be in a superposition state during the computations. But once you measure them or look at them, they can only be 1 or 0. They cannot be both in the same time. Okay, so let's talk about those magical qubits. There are a few differences between qubits and classical bits. One of them is qubits can exist in superposition in the middle of computation. The other, and maybe for me is the most important difference, is that qubits are physically there. Okay, when we think about classical bits like the 1 and 0, in turn, they're not actually there, right? They represent something, which is the current passing in a wire, right? So if there's current passing in a wire, that's 1. If it's not, it's 0. But qubits are actually there, like we build them, we put materials together to make a qubit. So it's a physical thing. You can touch it, of course, because it's kind of like a breaded board. But it's unlike classical bits, which are kind of like, if you thought about it, imaginary. This picture here of an IBM quantum computer. I think it's a very old one, and that one has like it has 4 qubits, which are the square thingies. So these are the qubits, and the zigzag things between them are the connections between the qubits. Okay, so I guess it's very important to know that qubits are there and they can exist in superposition. So the way to differentiate them from classical bits, especially when we're writing stuff, like writing stuff down, we use something called the direct style or the Ket notation. So in classical, we just say 0 or 1, and that represents a classical bit. To make it different, the quantum bit, we use Ket 0 or Ket 1, or we call them state 0 and state 1. So we call it state, okay? So that's qubits. Let's talk about the other cool thing, which is entanglement. Okay, so entanglement is one of the physics phenomenons that is very complicated to explain and even to wrap your head around, because it's like, what does that even mean? As I told you, qubits exist in real life, and there are different ways to create a qubit or to make one. IBM currently doing is superconducting qubits, which mean they take materials and make them superconducting, or the material themselves are superconducting in nature, and then they use those materials to form qubits. Some companies are using something called the ion trap to create qubits. So the creation of qubits lies on the hardware side of the quantum computing, which is actually dealing with materials and their properties to create qubits. There are way more than just iron trap and superconducting qubits, but I feel like they're the most two talked about ones. So what is an entanglement? So as we just said, qubits can exist in a superposition state. When they exist in a superposition state, they kind of like complete each other. Okay, they have to be kind of like doing the opposite thing in order to attract and complete each other. That is basically what entanglement is. Entanglement says make sure that when you have a qubit, you know that the other one, if it's entangled with it, it must be the opposite. One of the most famous way to explain this is like qubits, photons or electrons in an atom can be used as a qubit. So every electron will be a qubit. So if I have two electrons that are entangled, electrons kind of like the solar system, like there is like a nucleus, right? And there is like the electrons are like looping, and they have like a rotation, kind of like the Earth rotates around the sun and around itself in the same time. So if I have two, let's say, entangled planets, which is not really a thing, but just like to make the picture clear, then the Earth, for example, will be like rotating clockwise, and let's say Mars will be rotating anti-clockwise. That means that they are entangled. That means if I know what direction the Earth is rotating, I can for sure know what direction Mars is rotating because they have to be the opposite. In practice, to make entangled qubits, usually we create qubits using lasers or light source. If the photons or electrons are emitted from the same light source, they usually are entangled with each other. Of course, you can create like infinite number of entangled qubits in the same time. It doesn't have to be like just two, one up and one down. Sometimes there you can create 100 with different angles of rotation, and so they're entangled. I hope things make sense so far. The reason I'm saying this entanglement part, although like from a coding perspective, you don't actually have to think about entanglement much or superposition, maybe a little superposition. Qubits is the main concern when you code things. It's just that knowing those three pillars, I call them the three pillars of quantum computing, then you understand kind of how quantum computing works, and then you can use these concept to create algorithms for quantum computing, which is not an easy task. But if you're into creating algorithms, you just need to know the basic knowledge of those three pillars of quantum computing, which is like how a qubit behave, what is superposition, and how can two qubits be entangled. Is there any
Awesome.
questions, Sarah?
Yeah, I was just about to tell you. Yeah, so we
Yeah.
have a few questions.
Okay.
Yeah, so the first question is asking, does AI use quanta? Um,
Hmm.
so yeah, that's the
Uh,
first.
well, right now, no. But in the future, quantum do have a big premise of being used in data science in general, like in machine learning or AI. But at the moment, no, because at the moment, you can simulate a quantum computer. We're going to talk about that in a bit. But unfortunately, there is no quantum computer right now that's powerful enough to actually do. There are research about it, but there isn't actually a build application of it, if that makes sense.
Interesting. Okay. Okay, someone else asked, how does entanglement in qubits relate to how we do computations? Um,
Mm,
that's just asked, yeah.
Yeah, that's a very interesting question, but it would open the discussion for a lot of things. Have you ever heard of teleportation? I know it's a silly question because who hasn't, right? So, entanglement is what allowed teleportation to. I had once a entanglement does is like this. It's like imagine you have two shoes, like a pair of shoes, okay? You have pair of shoes. Because they were made from the same factory at like the same time, they're entangled. Here's what entanglement can use it. Theoretically speaking, of course, that haven't been made yet, although there is a lot of research in doing like teleportation. And by teleportation, I mean of data, not of people. Okay, that's why it's still a little bit maybe futuristic. But so we have this pair of shoe. If I take one and give Hala one, theoretically speaking, because they're entanglement, if I were to put something in the pair of shoe I have, it will appear at Hala's pair of shoe. Why? Because they're entangled. So here, entangled gave us something that wasn't there before in classical computer, which is the ability to transfer data almost instantaneously. Like if I just put it in the shoe, Hello did it in the exact same moment I put it in. Of course, this is a little bit still complicated and it still does not work in reality 100%, because in a sense, to make sure that Hallie got whatever I put in the shoe, I have to call her and say, hey, did you get it? And this calling her and saying, hey, did you get it? Is I'm going to be using a classical or an analog channel, like a cell phone or like a landline if I still have one. Of entanglement is faster than light communication. However, it will never really be true because you always have to make sure that the thing arrived where you send it. And to do that, you're probably going to need a classical channel, which is never faster than light, so it's never going to happen. But teleportation is one of the big things of what entanglement mean in quantum computing. I hope that answered the question.
Awesome, thank you. One last question. I mean, other comments are saying that this is very interesting and it's exciting them. One question is, can quantum computers help us in understanding quantum physics? So, what's your input on that?
Uh, uh, that is a very difficult question. I would say yes and no. I mean, you kind of have to understand quantum physics to build a quantum computing. Let me ask you a question. Maybe because all of you are computer engineer, or like most of you, and computer scientists. Let me say, do understanding how to code well make you understand how the hardware of the computer is built? The
Yeah,
simple
that's
answer is
yeah,
no, right? There's a
yeah,
lot
yeah.
of programmers that don't know anything about logic gates, which is how everything eventually translates to, right? That is the same idea. You can use programming to understand what's underneath, but usually people don't, because there is a reason that developers or researchers created like high level programming languages like Python and C++. You skip this step where you have to understand all the physics stuff and let's say the currents and all this stuff to actually code an actual computer, right? However, if you know the opposite, so if you're from the physics side, does that mean you're good at programming? Again, the answer is no. You can be, but sometimes you don't actually need to know all the steps to make something happen. You can just know one step. Can it help you understand the future step? A little, but it's not like a must. It's not like if I know how to program a quantum computing and then I understand quantum physics. Maybe the exception of that is if you know how to design quantum algorithms, which is a very complex thing, then you understand quantum physics. One thing that Hala said in the introduction that I really liked is like she said we give you some example to close the gap between practice and theory, right? It's a very big gap, and it's even bigger in quantum because quantum is not actually new. It's actually a very old thing since I think it was 1880 or 1980. It's been there for a while, but the people who've been working on since till like 20 or 50 years ago are physicists, and those physicists and they put them in very beautiful complex math equations, but they actually never thought about how can I code that. It's one of the things that is actually a very active research area right now, which is how to take this theory and convert it into practice and see if it actually holds. So there is a lot of promise, right, that quantum is going to be better and it's going to beat classical computers based on some equations and theory work. But is that really true? Is it going to beat it everywhere? Is it not? So one of the active research area is taking this theory and trying to code it and even simulate it, since we don't kind of have a 100% working quantum computing. And after they simulate it, they discover a lot of interesting things like, hey, the complexity and all the promises from the theoretical part does not hold 100% when we actually run them or do them in practice. So yeah, you knowing quantum computer can help you with quantum physics, but it's not like 100% you're gonna understand quantum physics if you know what quantum computing is. Sorry, that was a lengthy answer, but yeah. Any other
Thank
questions?
you, Sarah. Some, comment discussions are going on. Someone was
Okay,
talking about a chess engine by IBM named Deep Blue challenged the world champion and it won, but then it also lost another game. So how is that
yeah.
possible for an engine that calculates 200 million positions per second to lose to a human with very limited thinking? And people are really just debating in the chat. So someone
Let me
said
just say
because
one thing
yeah,
about
yeah,
that.
yeah, yeah. Go ahead.
There is no computer that's better than the human brain. They're faster in calculating things, but human brain will always beat in logic. There is a reason why we use complex codes to explain to a computer to do a simple thing like adding two numbers. Computers are not smart, they're actually very stupid. And that's why we have to very explain everything in detail for them to know what they do. So yes, they can calculate things fast, but they do not know why they're calculating the specific thing in this specific way. They don't. Person does. That's why, well, the human brain is the best computer out there. So
Awesome.
yay,
Okay.
humans.
Yeah. Awesome.
Okay,
Okay. So the other questions are actually more general. So someone asked
okay,
if you recommend specific courses or internships to work on quantum computing. And
sure.
someone else, yeah, okay.
We'll answer those in the end. Okay,
Yeah,
like
yeah,
the
I was
general
gonna
ones.
suggest that. Yeah, okay.
Okay,
So we'll keep those for
so
the end.
let's keep going a little bit and then we'll pause again for questions. Okay. So, as I told you, quantum computing right now, well, I would say right now is the best time to join the field if you're really excited about it. And the reason why, maybe there are so many reasons, but the most important reason why is right now, I would say it's the golden era of quantum computing because it's finally transforming from theory, pure theory and math, to actually practice, which is you can write code and run them on a quantum computing. So it's like, it's very exciting. So how can I write code on a quantum computer? So here, uh, before I continue, like I have all the material, like this notebook and all the codes in it is on my GitHub. If anyone want to access, I can send the link to Hala and she can share it with you. But it's like very simple. So yeah, it's there. So don't worry about taking notes or well screenshots. I can send you all the materials later. One of the things that I just wanted to share with you to tell you that it is actually a very active research field and actually industry field, not just research, is that there are now so many things that tools that you can use to write software for quantum computing. So this session is mostly focused on software, right? I'm not going to talk about the hardware part much, mostly because it's not my area of expertise, but uh, it's a little bit more complex. And if you want to know about the hardware part, we can do that. But for today, we're just going to talk about software. Probably the most used programming language right now to program quantum computers is Python. And Python is a classical programming language, right? So everything that we use today to program quantum computers using Python are add-ons that then gets translated to some kind of electrical pulses that people use to control a real quantum computer somewhere. Depends on what company you're using or what Python library. Unfortunately, not all companies are willing to let you play with their quantum devices, maybe because they're super expensive or for many other like reasons that let's not get into. But there are some companies that are willing and open to let you try at least some of their quantum devices like IBM, D-Wave, and Rigetti, I guess. Google, unfortunately, is very secretive. You can't play with their quantum computer unless you work there. So, but for example, the language we're going to use today is Python, and I'm going to use Qiskit, which is an IBM open source quantum programming library. And the reason I'm using it because it's probably the most famous one, and also because it has a very active development community that is very supportive and can help anyone who just want to jump in and like help with the code or learn new programming stuff. So developing a library on top of a classical language like Python or JavaScript or C++ or Java. Now, this is one option to go when we want to program a quantum computer today. But if we look for the future, will that be the best choice? Some people says no, some people say it's easier, to use the wheel than to reinvent the wheel. But some people did reinvent the wheel, as is they made programming languages that are specifically for quantum computers. And to do that, like there is here like Slick and Quipper. I think Quipper is actually built on C++, if I'm not mistaken. Oh no, it's own language. So Slick and Quipper, for example, they're new programming languages that are just made to program a quantum computer. Now, again, I do not know how technical that is, but if we think about programming a classical computer, the way you write it is you write in whatever programming language you want, and then all of that gets translated, compiled, interpreted, whatever programming language you use, to an assembly language code. I hope you all are familiar with assembly. So assembly is like the hardware descriptive language kind of thing. So it talks to the hardware of the computer directly. And oftentimes, as a programmer, like you think of Python or in C++ level, you don't actually worry so much by thinking about the assembly level or how your code interprets to hardware, right? But in quantum computers, since we still kind of like in the early stages of developing working quantum computer, not necessarily a classical computer, but on the quantum side. The the assembly language that is used for quantum computer is called the QAS, which is the quantum assembly language. So some people call it QASM, some people say QAS, whatever. The acronym just stands for quantum assembly language. So everything we write, regardless of the language that we use, a classical one or a quantum one, in the end, for it to run on a quantum computer, it has to transfer to this quantum assembly language. Okay? So enough talking. If you're technical people like me, you like coding more than chatting. So what we're gonna use today, as I said, we're gonna use a library called Qiskit. So to install Qiskit, you can just pip install it. And Qiskit uses matplotlib in case you don't have it, install it as well. So installing those two lines will give you access to run this code perfectly. Okay. So here, first in the code-wise, first thing we need to ask ourselves is like, how do I code a quantum computer? Do I do it the same way I code a classical one? Now, quantum computers, right now, it's still working on a gate level, which is like, classically, we're way far over that, but in quantum, we're still working on that level, which is putting a bunch of gates next to each other to make something happen. Okay, so to put gates in something, we have to put them in a circuit. So here's how we, if you want to do it, and some qubits stored in some registers. Again, this is low level hardware stuff, but that's where quantum is right now. So you have some register that has a bunch of qubits. The qubit, it can have qubits, and there's also classical registers. And classical registers are used to hold the value of the qubit after we measure it. Because for now, quantum memories are not really a thing yet. So to use all these things I said, we just from Qiskit, you can import quantum register, classical register, and quantum circuit. These are the thing I just talked about. And AIR and execute. So AIR is like the backend that provides by IBM that kind of does the quantum part of the code, and execute is just to execute the code. Now, when you use Qiskit, you have one of two options. You can either simulate the circuit, like use the or if you're really curious and you want to run it on a quantum computer, you can do that, which is use one of the IBM publicly available quantum machines. We're going to talk about that just a second, or how to access them. But here, for example, I made a quantum circuit that had 2 qubits and 2 bits, or 2 classical bits. Okay, it's a very simple circuit. Now, because quantum uses gates, so we need gonna take a stop look here and talk about gates. You guys are familiar with gates, like not gates, and NAND, not buffers. I don't know if
Yeah, I think the engineering part of the audience is definitely familiar in
with
general.
logic gate. Yeah. So for quantum now, that is the only way to actually build a circuit, is use the gates. So I'm gonna introduce you, I guess, to 4 gates. I think there are four or five. We'll see. And they're like the basic gates. There are more gates, and you can create your own gates actually, but that's like that's a story for another day. The first gate is the identity gate. The identity gate is like a buffer in classical computer. It doesn't do anything. It's just, it takes a qubit and it makes it stay as is. So if it goes in as state 0, it stays as state 0, and if it goes in as state 1, it stays at state 1. Okay, to add that to a circuit, so the identity gate takes just 1 qubit. Okay, so it takes one. So for here, for example, I said QC, which is the quantum circuit we just created, and I said .iden. So iden is the method that performs the identity gate, and I give which qubit do I want. Okay, so here I said, for example, put it on qubit 1. So again, just to refresh. We made a quantum register that had 2 qubits. And just like anything in programming, when you make a quantum register, I want you to think of quantum and classical register, or even quantum circuit, as a list of something. So in case of a register, a quantum register is a list of qubits. A classical register is a list of classical bits or bits. A quantum register is a list of gates. Okay, so think of it as a list of something. Why? Because then it will make sense that we index it to access a specific qubit. So if I want to access qubit 1, I will index 0 because it's programming, right? And if I want to access qubit 2, then I will say it's q of 1. Okay, so here means just show me, just I apply this identity gate to q1, which is like this guy here. You can draw the circuit, and Qiskit like draws cute circuits, if I may add. So here I applied the identity gate. Okay, technically I applied it to both of them, ignore the warning. And that means that this quantum register, all the qubits in it are initialized to 0. Okay, so 0 is always the initialization stage. Okay, cool. Now let's talk about another gate that does something. We're going to talk about the NOT gate. And just like the classical one, it's very equivalent to the NOT classical gate, which is flips a bit. So if you give it a 0, it gives you back 1. If you give it 1, it gives you 0. So here, so this one had the identity gate from before, and then I added the X gate, which is the NOT gate, and it flipped it from 0 to 1. So it was 0 here, it became 1. Okay, we're going to talk about what this one is later, like the one here, but in a second. We have something called a control NOT gate or a Toffoli gate. The control NOT gate is a NOT gate, but it only works if the control is 1. So if the control is 1, it's going to flip whatever you give it. If it's not, it's going to act as a buffer. It's like a controlled buffer. We also have those in classical. So I don't know, should help. A control NOT gate, unlike the NOT gate and the identity gate, is a 2-qubit gate, which means it takes 2 qubits, which is the control and the target. In the order control first and then target. So when I say CX or control NOT, the first one I give it is the control qubit, and the second one is the target qubit. Okay, remember from the last step, we made this first one, which is Q0, we made it 1. So now if I take this one and use it as a control to flip the other qubit, we found that we have 1, 1 here, and that is because this one is 1. Okay, or the control is 1, hence the target is flipped. Is there any questions so far about gates?
There are questions, but they're not directly related to gates. So if you want, they're more general. We can keep them till the end.
Okay, cool. Yeah. Let me know if something about gates or code pops up.
Yeah, okay. Yeah, of course.
Now, my favorite gate of them all, or the gate that actually make a difference. Like, I'm pretty sure all of you are sitting there thinking, is like, if we have the NOT and the buffer and the control NOT, why are we bothering doing quantum equivalent of them? Here's where the magic happens, the Hadamard gate. And this gate is the gate that creates the superposition. So you give it a 0, and it gives you a superposition between 0 and 1. And if you give it 1, it also gives you a superposition of 0 and 1 as well. So regardless, it's always going to give you a superposition of 0 and 1. So let's say here, so for example, here I gave it, as I just said, we always start from 0, right? So 0, and then it gets flipped, so it becomes 1. And then I use the Hadamard gate, which has this the H. And then I have this. And this state, I'm sorry, it's printed twice. It's because I was testing this wave function thing. So I had print inside it and print outside it. Anyway, but here I created a superposition between 1 and 0, but only for this qubit, which is the first qubit, which is this one here. And because the circuit has 2 qubits, the other one remained untouched, which is 0. Now, see those numbers here that I said I'm going to talk about in a second. Now, quantum computing is all about probabilities. You don't know what's the probability of measuring something, but you give it a probability. Like we talked about Schrodinger's cat. We said the cat is both dead and alive. It's 50% dead, 50% alive until you open the box. So here, since you only have one state, it says it's 100% this state because there is no superposition yet. We haven't created it yet. But here it says there is superposition. Okay, and usually the probability of measuring a state is the square value of whatever number is here. So this number actually is 1 over square root 2, right? Which is like 0.707. So the square root, the square of that is half, which means this is an equal superposition that give you 50% 1 and 50% 0. Okay, now since we talked about the Hadamard gate, it's create superposition, which is also creates entangled states. Talked when an entangled qubit, so we have to like emit them from the same light source, like the same laser or something. Now here, the Hadamard gate is going to act as my source. So any gate that comes out of it, it's going to be entangled. Okay. So there are 4 most famous, of course, there are so many more. The 4 most famous entangled states, or we call them the bases. We have the 0 base, which is like just 0, and then we have the 1, which is just 1, and then we have the plus and minus. Now the plus state, sorry, the plus state, the plus state is the result of applying the Hadamard gate to a 0 qubit, and it gives me this. The minus state is applying the Hadamard to a 1. Now, the only difference between them is this plus and minus sign here. And this plus and minus signs is, you can think of it like this. We just said that qubits is like actually a very complex thing. You can think of them, I do not know if like maybe I will use a math analogy because that's how I think about it. Think of a qubit as a vector. In math, a vector is something that has an amplitude, which is how tall it is, you can think of it, and what direction it's rotating in. So the difference between state plus and state minus is this negative sign, which is the direction of the rotation. So one of them like rotates left and the other one rotates right. Why? Because they're entangled. Okay, so they have to rotate in the opposite direction. Okay, now not talking about this, of course you can use code to build circuits right away. If you don't want to use code, you can use the IBM Q I don't know, or IBM Quantum Experience. You're gonna have to create a profile and then something like this will show up. Maybe not exactly like it, but like it. Now, here is the cool thing about creating it. It's free, so anyone can create a profile. Once you do, you will have access to actually IBM quantum computers that are available for the public. I have here more than what you will have because I work with IBM, so I have I think 4 or 5 devices that are available for the public and you can run stuff on, like can actually run them on a quantum computer and have the result back. Another thing is, what if I don't like to write code? And I know it's a weird thing to say because all of us are like in computer, but some people are not, and they're curious about building quantum circuits. You don't have to write code to build quantum circuits. You actually can use something like the circuit composer, which is here on the left-hand side. And you can just drag and drop some gates like this, and you're going to see the results. And remember when I said like every qubit or each state is kind of like a vector? See here this 3D cute implementation here. It's called the Q sphere, which is one of the way to represent states. You can see that like we have 2 states. And one of them is like at that angle and the other one at this angle. And it says, hey, you can measure this with probability 0.5 because they're just 2 states, so you can measure it with like equal probability. You can just click on it and delete it if you don't want it, like this. Like if I just have like just a NOT gate, it will say it will create like a state 001 because I have 3 qubits here. And it's with 100% probability because there is no entanglement, there is no nothing. You only have 1 state, so it's like 100% probability. Okay. One last thing to mention before I take question is how do we read the the state? Like where is the zero and where is the one? Uh, in Qiskit, the zero is the one on the left hand wall, the left side. But in here, it's actually on the right side, if you've noticed. So this is qubit zero, and it's actually on the right. It's flipped. It's flipped in Qiskit for some mysterious reason. Else, or you can just like take the Qiskit one like this. Like here, the way do I make it not flipped in Qiskit is I use this specific function in like another module. Again, the module is in the GitHub. It's just to make things a little bit simple, to make it look like this, which is how actually it's used in mathematical equations. Like you read it from the left hand side and then you go right. Any question before we kind of take like a kind of an exercise or an example of how to build a quantum circuit?
Yeah, there was a question related to gates specifically. So someone asked, the controlled NOT gate is like a NOT gate with an enable. So they were asking,
Yes,
yeah, okay.
exactly. So it has an
Mm.
enable. If the enable is one, then it's a NOT gate. If not, it's a buffer
All right.
in
Awesome.
classical terms.
Yeah. Okay.
Yeah.
Okay, great. Yeah, the other questions, like I said, they're more general about quantum computing in general. So we can do the exercise and then return to those.
Cool.
All right.
So let's do an exercise. So, or like an example. I guess the example is written here. So let's say I want to make a circuit that takes a 4 qubit state and flips the last one, which is like this one here, the fourth qubit, or the q of 3, if you want to think about it from a programming perspective. If it was 1, but if it was 0, it will do nothing. So the challenge now is to build a quantum circuit that takes 4 qubits and it only flips the last qubit if it is 1. But if it's not going to do anything. Now, first, of course, this is a general example. So whatever initial state or whatever you give it, the code should work regardless. It just flips the last one if it is 1, otherwise it does nothing. But we have to work with something, right? So let's work with this state as an example. So first I need to create this state. You can either, again, use code or use the like a circuit composer like here. There's more than just the IBM one. There's more like here in my what software you can use to program quantum computer. There's other stuff like I think like QGS. You can use the circuit simulator, and there's a QS circuit simulator. There are so many if you want to use from, but I just I don't know. I like the IBM one, and it's always developing, so it wasn't like a big deal. Okay, so I want to create the circuit 1011. So I want to start from the zero. So I'm going to start here from the top. Okay. So I need 4 qubits. So if I just add on this, click on this plus, then I have another qubit. Notice here that this C, it says C4. It just says that there is 4 classical bits there if you want to measure something. So I'm going to make 1, right? 0, 1, 1. Okay. So now I have the stage 1011. Okay, again, when we read it here, we read it from right to left. Okay, so 1011. Cool. And here it tells you how it shows in like a 3D dimensional thing. Cool. Now I made this circuit, or make this initial state. Now I want something to flip this last one only if it's 1. So we can think about it like this. I want to first check if it's 1, and if it is, flip it. How to check if something is 1? Here I use like 2 control NOT gates here, like they're flipped. Let me tell you how to flip them. I actually used another qubit. Ah, okay. We'll get to that later. So the 1011, and there is the Q4 here. Sometimes when we perform stuff in a quantum computer, we're gonna need more qubits than, I don't want to say than we have. Like we use some extra qubit, kind of like dummy variables in classical computers. So here I have another qubit, it's called ancillary qubits, which are dummy variables in classical computers. This qubit, I'm just going to use it to check if my third qubit here is 1 or not. The way to check is if I applied a control NOT gate here. What does that mean? I'm saying, hey, if this is 1, right? Like here after the NOT, if this is 1, it's going to flip this, right? Because this one is like 0 by default, right? Everything is 0 by default. If it is 1, it's going to flip it. But if it's not, then nothing is going to happen. Awesome. And then I added like a flip one like this, right? You can like change the direction of it like this. So here it says which one is the control, which one is the target. I can just say I want this one to be the control, and then it flips it. And if you go back, it's flipped. So here what I'm doing is I'm checking if this one is 1, then it's going to flip this Q4. And then I'm going to use the result and flip the Q3. I know it's like very weird. It's like you're using it to flip itself in a sense. So if Q4 now is 1, that means that Q3 is 1, right? Because otherwise Q4 would still be 0. So only in this case will this be 0, or will Q3 will be flipped. I don't know why it says it's not the limit. Internet is not the best. We can just go to the code and see how it works. Okay, so using the code, I apply these qubits. Like I have to write code that does every gate. And notice that when you create a quantum circuit, every time you add something, it keeps appending to the end of the circuit. That is very important. If you want to start all over, you either have to define a new quantum circuit or like delete everything, like reset the circuit in a sense. And here I'm going to say, what is it? Like here I'm going to say measure it, measure this. And notice here that I say I only want to measure 4 qubits. So the reason is that I don't want this ancillary qubit to show up because it's just going to confuse me, right? I'm just using it as a just the first 4 qubits, which are the one that I care about, and tell me how much it is. So this is the result, which is 1010. And the reason we got this result is because we initialized this to 1011. If you would have removed this X gate here, then the result would have been the same. So the input state will be 1010, and then the output here will be 1010. Nothing would change because only do something if this Q3 is 1. One last thing to say is this shots here. What are these shots? So quantum computers, even in the simulator, are kind of faulty. Okay, like they have a lot of errors. And one of the way to kind of overcome the errors or avoid them is to repeat the same circuit a lot of times and take an average of the results. So that's what shot is. It's like how many times do you want to repeat the circuit? So here I said like 1024 because it's like an average number. You can do more or less. When you run on an actual quantum computer, it's better to do more, like 5,000. So because they're more faulty than the simulators, so they need more trials to get something right. Finally, so here is to measure it. So this is like this black thingies are the measurement, okay? And finally, you want to execute it. So you can either execute it on the quantum simulator, and again, you give it how many times you want it to be repeated, and it displays here. It tells you I'm going to get this state. As you can see, it's flipped like the IBM Q experience, which is 1010 with 100% probability, so all with probability 1. If you want to run it on an IBM device, like an actual quantum computer, you're going to need to use the name of that backend. So for example, this one is called IBM Manhattan. So what you're going to do here, instead of writing Quantum Simulator, you're going to say, for example, something like this. Let me copy this. And so instead of Cosm, you're going to say backend. Okay, backend. And then you're going to write the name of the device here. Again, based on your your membership, I guess, you're gonna have like the ability to use more device than other people. But if you're just using the general available for public devices, then like when you create something, it's gonna tell you, hey, it's gonna give you a token that you have to put in the code to validate that's actually you. And then you can run it in a quantum computer, a real one, and then it will give you the results. Same way. Uh, Before we finish, let me just talk about the devices here for a second. So here is the devices that IBM now has, well, or has and given access to it to my research group, which is the IBM Q Hub. It's like this map tells you how many qubits have, and it's got this QV. QV stands for quantum volume, and quantum volume is a way of measuring how good a quantum computer is. QV32, that means it's a quantum computer that is good enough to run a circuit that has, let's say, I'm not going to say 32 gates, but I will say 32 gates. Let's just simplify things. It's not very complex. 32 is the best that quantum computing can do now, which is not much. It also depends on the gate and the machine itself. And that's a topic for another day, I guess. But here, as you can see, there's so many of them. I have like 18. This is the simulator, which is the one that everyone uses by default. So you can see here, there's one person now that's running stuff on the simulator. And then here you can see like the other machines, how many people are waiting to run stuff on it. It's probably like the one that's full because so far IBM Q Paris is like the best quantum computer that IBM has at the moment. It has the lowest error among all of the devices that they created so far. I didn't play with the Manhattan and Toronto one. Maybe I will do that, but for the one I played with, it's like the IBM the IBM Q Paris is the best. So yeah, so that is it for me. I now will answer questions and maybe any concerns you have. Yeah.
All right, awesome. Thank you so much, Sarah. This was really interesting. So I actually did not know any of this. So I'm personally interested, and I bet many others are reading.
Yeah.
So yeah, thank you. Let's do some questions. Someone asked, like, let's say this is more direct to what you just explained. What
Yeah.
causes these errors? So what causes these errors that you were just talking about?
Awesome. Great question. So, as I said, now since qubits are something that to be made, it can be faulty for so many reasons. Qubits are very sensitive to noise. And noise as in like waves, like microwaves or any waves that happen next to the quantum computer when it's running something. And since you can't actually have an environment that doesn't have any noises, there's always going to be noise due to like waves or like microwaves or like phone waves, any waves that's kind of like touches the qubit when it's doing its thing. Another thing, the qubit itself can be faulty by like when it's constructed. The gates are faulty as well. Like the gates you apply are faulty. One other thing, let me go to a device with not a lot of qubits. The connection between the qubits. If I here open like different ones, like see this is the Rome one, okay, and you see there's the small errors between the qubits. There's already connection between the qubits, which mean can qubit 4 connect to qubit 3 or not? Uh, if I open here the Bears one, they have this special architecture of the qubits. Like the Toronto one has this one. If I open a different one, it will be different. So what does that mean? Let's say I apply the same circuit with the same qubits. Like let's say I have a circuit that applies a C0 gate or a control node between 0 and 4, between qubit 0 and qubit 4. Now, like in this case here, there is no direct connection between qubits 0 and qubit 4, right? It has to go over a lot of other qubits to get to qubit 4. By the time the signal goes all this way, it's going to be faulty. It's going to decay. If I run the same circuit on like the ROM device, it's going to do the same thing. If I run it on the here one, the Santiago device, it's going to do the same. The Barris one will be a little bit less faulty because now between 0 and 4, there's only 1. See? For now, the performance of any quantum algorithm you write code for depends heavily on the hardware that you're implementing it on. They're trying to move on from that and create codes that are independent of the hardware, but for now they are very dependent, and that is a cause of error. There are so many other errors. Like, see here, for example, it says, hey, the C naught error is like this much. It's not very big, but if you have like 100 C naught gates, you're gonna find that the error accumulates, and in the end, instead of having a state with 100% accuracy, you're gonna have it with like 60% accuracy. We can talk gates.
Okay.
There are so many kind of gates. Sorry, of errors. We're not going to talk about them because it's a very big topic, but there are so many reasons why there's errors in hardware right now.
Awesome. Thank you. Okay. Another question is maybe it's related, but I'm not sure. So why are quantum computers? I'm sorry. Why are quantum computers more faulty than simulators? So um, yeah.
Okay, so as I just said, so when you run something on a real device, you have this errors from the noise, right? And you have the errors from the qubits, and you have the errors from the gates. Like, so there's three kind of errors. However, simulators are programs that's built to kind of imitate how a quantum computer would behave without the error. So that's why the simulator will give you the perfect results, or the results if you have 100% accurate working quantum computer. That's why the simulator, usually you do with the simulator first to see what is the accuracy. Like if I run the same circuit on a real machine, it will give me 100% probability. It will measure it with something, and then there will be other states that it will you could get a measurement of because of the noise. It depends on your luck, really. So
Okay.
yeah,
Thank.
okay.
Yeah. Okay. So another question is: classical computing took decades to reach where it is today. Will it take quantum computing more or less time to do so? So this is more general, I guess.
I hope less. Let's
Okay.
just say I hope less. Because we already been through the process, right, to make classical computers. It should be less, but again, there are a lot of difficulties that show up that is not that we didn't predict, but hopefully less. Will we have a real running quantum computer in 50 years? Maybe. People would say no, some people would say maybe. No one would say yes, though. You can't guarantee it.
Okay, okay. Okay, so another question, isn't using a language specifically designed for quantum computers much more efficient than using classical languages? So I
Yes.
believe here is referring to the Python and
Yes,
yeah.
it is. However, the reason that a lot of companies or a lot of developers are using stuff built on top of classical computer is to make the accessibility for quantum computer easier. Now, I want you to think about it from that perspective. If I say, hey, I will hire you to do some quantum computer work, will it be easy for you to already know the language you're using and just learn the quantum side, or to learn both in the same time? The easier is to focus on one thing, which is learning the concepts of quantum, or like how to deal with quantum computers. And that's why people are using classical stuff for now, to just make it accessible for everyone who's curious to learn or to use quantum computers. Once you're comfortable with gates and how to transfer algorithms from a mathematical thing to like gates, you can use the languages that is specified for quantum computing. It has a little bit weird syntax, not like the classical programming languages. Feel free to check Slick. It's also it's in my list here, which is a very new programming language for quantum computer. Not everyone will be very happy with how it looks in the beginning because it's a little bit weird. That's why people use classical for now. But yes, as the field further or go further or develop further, then we'll probably let go of like using a classical channel to program a quantum computer.
Yeah, okay. Thank you so much. Okay, so let's see other questions. Um, okay, so I have to scroll up just here. Okay. So someone asked, what knowledge do I need to study quantum computing? So like maybe prerequisites or something. What do you
I would say you do not need any knowledge except a curious mind. I did not study theoretical physics or mechanics. I
All
just
right.
knew classical computer and I was like, I want to get into quantum because it sounds like fun. And that's what
Yeah.
I did. You learn on the way. You do not have to have pre-existing knowledge.
All right. Great. I'm sure many people are thinking the exact same thing now. So yeah, that's interesting.
If you know a
Um,
little bit of math, it will help. Linear
yeah.
algebra. It will help. But is it necessity? Not really.
Okay. Great. Okay. So another question is, do you yeah, we mentioned this before and we said we're gonna keep it till the end. So do
Yeah.
you recommend any specific courses or internships to work on quantum computing? Let's say courses or resources in general.
Uh, well, okay, that's a there are many resources available online, like in Coursera or ADX, uh, of like quantum quantum courses. The way I learned it is so this Qiskit, there's something called the Qiskit book. Okay, let me. So they have a book or Qiskit textbook that explain everything from the beginning to very advanced topics with code at all. And I really like from what is quantum to like what is a qubit gate, the one that we been through, and some further gates and how to run them and what they mean and their mathematical representation. I think this is a very good source. Another source I used is also Qiskit has a YouTube channel and they host a lot of professors that works on quantum stuff and they explain specific topics in quantum computing. So that's a also is a good resource to learn from. But I would say to start with, I think like this Qiskit textbook is a very good place to start. It tells you what the math you want. It's very simple. Yeah, I liked it.
All
Fits.
right. Okay. Yeah.
Yeah.
Okay. Yeah, so thank you. Let's see anything else. Someone asked, is it possible to make portable or commercial quantum computers in the near future? I think you've already mentioned this.
In the near
Um,
future, no.
yeah,
The not so near future, hopefully.
yeah, hopefully. Okay. Another one is, or like a continuation of this one was, and why do quantum computers need such massive cooling rigs?
Awesome. So not when we talked in the beginning, we said that there's so many ways to make a qubit, right? So this massive thing that you see here, I mean, this all the fridge, the quantum part is actually the little thingy in the bottom there, but all of this is fridge. You will ask, why do I need all of that? Now, this is the IBM quantum computer, and IBM uses superconducting qubits. And to make a material superconducting, it has to exist in very low temperatures. That's why they have this fridge, because they have to keep the qubits in a specific temperature for them to act as qubits. Now, not all construction of qubits require this fridge. Like the iron trap one doesn't require it as much. Researcher and like materials and material science are working on constructing qubits that works in like room temperature. If those qubits work, then I think the probability of having a commercial or like something a portable quantum computer will be higher. So not all quantum computer needs the fridge, only if they're using superconducting qubits. Yeah. That's
Yeah,
why they have.
okay, great. Okay. Someone asked maybe a more general question, what chemicals do we use for creating a qubit?
Uh,
Are there specific, is there an answer for this?
it's more like what materials to use. Again, we use superconducting materials. So if you're into chemistry or you're a chemistry major, you probably knew about superconducting materials than me. It does use some chemistry and like injecting materials. I do not know, but silicon is one of the things. For example, silicon is a semiconductor, right? It can be a superconductor at specific degrees to create qubits. But honestly, further details about the construction of qubits, like I cannot be very, like, I cannot give you much knowledge about the chemistry of it.
All right, awesome. Okay, I think the same person asked, how was your research with quantum computing and how many papers have you written? So you want to talk about your career so far in quantum computing? Sure.
Sure. So I've joined actually quantum computing a little bit. I actually joined in April 2019, so actually not very long ago, like a year and a half, you can think of it. So a year and a half ago, I have one paper published in that year and a half. Uh, it was a very interesting year. I've learned a lot. I got into quantum with zero information about quantum, with zero knowledge. I just loved the programming. I like Python because, well, what's not to like? And I was like, I want to do quantum. So it took me some time to wrap my head around the basics of quantum, about how things are, and then my the paper I published. I can uh, okay, I can open the archives for you. It's like there, you can access it. It was about applying a quantum computer, or like using the different devices and the simulator to solve an NP complete problem, which is the K clique problem. I don't know if you know what it is. It's a graph problem. But if you
Yeah,
want
yeah,
it,
I'm familiar.
yeah,
I
if you
don't know
want it,
about anyone else, but yeah, this is really interesting.
so you can read the paper. It will be published next month also in an IEEE journal with a little bit more modification than this version, but we used it to solve an NP hard problem to see if the speeds up really. Now, the reason I wrote this paper, or the reason I did this research, so or like apply what you learn while you're learning it. It's the best way. And one of the things that is exists now in quantum is like there is a huge gap between theory and practice in quantum, unfortunately. And as I mentioned earlier, one of the complex things is you have a lot of theorists that has these algorithms that has amazing complexity versus the classical. And then you're like, hey, if I interpret this equation into a circuit, will that like give me the same complexity? And this research was to show that it doesn't. That things get more difficult when you kind of move them from theory to practice, and when you move them from practice, which is just pure code in a simulator, to actually run them on an actual device. Yeah. So this was what I did. This paper was the result of what I did like last year. This year I've been working on something new, but I haven't published anything about it yet. It's I'm still in the beginning, which is if the one of maybe I did not mention that, and I do not know if you guys know it is. So here, like qubits exist in superposition, right? Unless you open the box or measure them, then the superposition breaks. 100 gates, and I want to make sure that it's working the way I want. In quantum, you can't actually like stop the circuit in the middle, measure it, and then make it continue. It will not work again, or it will start. Take a peek inside the circuit in the middle and see what's happening. All measurement has to be done in the end when there is no more circuits that can be like no more gates to be measured. You can think of it like this. Okay? But if you thought about this for a second now, how can I debug a quantum code if I cannot measure in the middle or I can't run it step by step, right? So that's actually my research topic for now, which is how to build a debugger for a quantum circuit if you cannot measure in the end. And so it takes a lot of work. It's my PhD thesis, so of course it's going to take a little bit more than 6 months to do something useful with it. But yeah, that's what I have for the published. Not much. I haven't been in quantum much. Just hopefully I'll publish more soon.
Yeah, yeah. We look forward. It's super exciting. Honestly, everything you're talking about is like, taking everything, basic stuff that you know, and then putting it all in this like higher level of quantum. Sounds
Yeah.
awesome. So for now, we have only one question left, and it
Okay.
is, Yeah. So, are there careers for people in the quantum physics theoretical side? In theoretical physics.
Oh yeah.
Yeah. Okay.
Well, yeah. If you're into the theory, then oh yeah. And if you're into a theory, if you're a theorist who can actually explain things in practice, then there is more demand for people like you, the people who can touch on both sides,
Awesome.
right?
Okay.
Who can do physics well and also can do practice a little bit, so they can kind of like help build this, like build this bridge to close the gap between theory and practice. So yeah, there is a lot of internships. So there was a question about internships. I don't know about Google, but I know that Microsoft have quantum internships. IBM has quantum mentorships for undergraduate levels people. If you want to be a PhD student and then you're interested in quantum, there is a lot left to be done in the field to get it to where classical is now. So there's always the demand for more people working on quantum. So yeah, the opportunities are out there. You just have to find them.
Great. Great. That's a great note. Okay. In terms of questions, we're done. I mean, more people are saying that this is very interesting, and yeah. So thank you so much for this. It was awesome. Do you have
Thank
anything
you for
else?
having me.
No, it was actually our pleasure. You were awesome. I love this event. So
I'm
this was
happy.
amazing. Okay.
I hope it made sense. I hope it was a nice introduction. And I hope you
Yeah.
guys keep reading about quantum and it that sparked your interest to actually get into the field because it's very exciting and now is the best time to join.
Yeah. Yeah. Great. Okay. All right. So, oh, actually, one last question. Someone asked,
Yes.
can you talk about your learning journey from Alexandria to Japan? So,
Oh,
how?
sure. I mean, I finished my bachelor in 2014. Wow, 6 years ago. Wow. Although it's very long time, I you can think of it as like, oh, I feel like it was yesterday when I was like in my senior year of undergrad. The reason I decided to not continue studying in Egypt is because Egypt, like many other countries, are not very supportive for people with passion. They're supportive for specific people. It's either you have money or you have like, hey, like I'm very exceptional. But let's say I was curious. I always loved studying. I didn't like the education system in Egypt. It's flawed, and I was in a public university. It's not the best. It's not very encouraging or nurturing of individuals. It's just a mass production of education. You can think of it like this. And I wanted to go somewhere else, somewhere where people are judged based on their interests and not based on their gender. Unfortunately, Egypt is a little bit sexist. So I was like, okay, uh, where to go? I did apply for so many other countries, not just Japan. I applied for countries in Europe, in the US, and for Japan. And I got accepted actually in the US, in Switzerland, and in Japan. And I chose to go to Japan for one reason. It felt more adventurous. Japan was always this cool country, right? Like it's cool things, right? And I was like, yeah, it was that cool from the perspective of the technology that they offer, in addition to cool from the perspective of it's exotic. You can think of it. Also, it's a very safe country to live in, which was very important in my decision making process. Did I know Japanese before I went to Japan? I did not. Do I know Japanese now? Not very fluent in it, unfortunately. The school that I went to, or the two schools that I went to in Japan, like the one for my master's and now for my PhD, uh, to study or to conduct research, you really well, my master's professor, she was a Japanese professor and she spoke fluent English because she lived in the US for a while. And the classes were in English. There was, of course, classes in Japanese, but you don't have to take them. You can just take the English classes. And my school, which was Tokyo Institute of Technology, it's a very international school. There was people from all over the world, and they speak English, so it was cool. You don't need Japanese as much as you would think. There was chances to learn Japanese, which I took, but Japanese is one of those very complicated languages. It's not as simple as English. I tell you that. It has three alphabets. One of them has more than 2,000, like, I don't know what to say, character. So yeah, it's not that very simple of a language to learn. You have to dedicate a lot of time to learn it. And if you're there doing research and taking classes and like working part-time, you will not have enough time to dedicate to be fluent in the language. But I know enough to get by in Japan. And then after I finished my master's, I did my master's on actually something called approximate computing, which is kind of a futuristic approach to computing as well, which is okay. Let's say Moore's law, which is the transistor is going to keep getting smaller and smaller, is going to stop sometime soon, right? What are we going to do next? There are so many answers to that question of what to do next. One of them is something called approximate computing, and approximate computer saves energy and execution power by kind of inserting error in the code, and at both hardware or software level, or both. So if you will, like, let's say a simple example, let's say I have a loop that iterates 1,000 times to get me something. If I made it iterate just 500 times, will I get something close to the thing I want? If the answer is yes, then just made it iterate 500 times. Now I know this sounds like very minimal because approximate computing is something that can only be applied on like a large scale thing, not like in a personal scale, like in storing and retrieving data from the memory, which takes a lot of electricity than you would imagine. So that I worked on that side, and also worked on the software perspective, which is like how to analyze software to know what variables are not needed or do not contribute so much to the accuracy of their end result of the code. So if so, we can like use some approximation on them. Kind of like if I have, for example, a float, can I just make it an integer if it's not that important to save memory, and hence the memory, like the connection to the memory time and the electrical power needed to connect to the memory will be less. On a large scale, this will be like very efficient, but on a personal scale, you will think it's like, what? How does that matter? I mean, my code run very fast if I made it an integer or float. But like if you're a very big scale company like Facebook or Google, which they spend a lot of money on like electricity just to for the data centers to communicate with data, to store them and retrieve them, something like that would save them a lot of trouble. So that was my master thesis. And although it was exciting, I didn't like it. I was like, okay, this is not bad. I accepted to do it in my master's because I could do it. So I was like, yeah, whatever. I just want to go to Japan or go to another country. So sure, I'll just do whatever I can. But during my master's, I learned a lot about a lot of things, not just what my master research was about. And one of the things that got me curious was quantum computing. So I attended a physics class, a quantum physics class, that didn't have much math in it. The professor was American, and he was very great at explaining things from a logical point of view, not a mathematical point of view. And it got me curious about this quantum field. And so I started reading about it, and started like I communicated with that professor from the physics class a lot about how I want to learn more about quantum and such. And in the start of my PhD, I did tell him that I wasn't very happy with my PhD topic and I wanted to change things. So he introduced me to his friend, which is another professor, which is my current supervisor. And he is an engineer who lived, who did classical